Hi, this is Jeff from the Ozark Mountains, that's in Missouri, in the USA. Today we're going to talk about what we can do at home to be able to plug something into an old vintage computer when the connector is long since obsolete. So let's get started. Thanks to PCBWay for sponsoring this video. They do circuit boards of all sizes, small circuit boards, medium circuit boards. They can even assemble them for you. Are you a maker who likes sharing your ideas with other makers? If so, you can submit your articles to the monthly submission for PCBWay and earn coupons and notary titles. Check out the link in the description below. A situation we've probably all run into messing with our vintage computers is we want to plug something into one and it has an odd connector. And, it may be long since obsolete. It may have been a proprietary connector. And what do you do? What are our choices for trying to connect this to the outside world? Given the passage of time, any connectors or cables that were available back in the day to plug into our old computers have become rare as hen's teeth. Now, you might be able to find an old cable and cut the end off of it to connect your own thing, but then you're destroying an original cable that you might want to have used to plug into an original accessory if you happen to get one later. Getting a connector professionally reproduced is very expensive to pay for all the tooling and the design time. So what do we do? Luckily, in this day and age, we have a lot of capabilities at home that 20 or 30 years ago we could only dream of. We can 3D print parts, we can get circuit boards made, etc. So we can do a lot right from our homes to try to reproduce some of these connectors. So in this video, we'll be covering the process that I did to develop a connector for the Casio bus, specifically for this PB100 or Tandy PC4. It's a 12-pin Casio expansion bus. And then toward the end of the video, we'll cover a couple mains connectors that Sven Petersen made for some vintage equipment. A while back, I got this Casio PB100, which is in great physical condition, but it doesn't work, and it turns out that the 2K static RAM chip inside is bad. I then found a Tandy PC4, which is the same unit, branded for Tandy, and luckily, this one works. It got me to wondering, maybe what RAM chip this was and if I could just replace it. And sadly, you can't do that. They use an odd 4-bit static RAM chip that was made by Hitachi specifically for Casio that works on the Casio 4-bit bus. And of course, we can't buy those chips anymore. So I got to wondering, well, I wonder if we could, make something that would work out of modern components. And luckily, I found Piotr's website, and he had several years ago decoded the Casio bus and did an excellent write-up. I will put the link to his webpage below. And, thanks to his work, that gave me the impetus to try to see what I could do to maybe create a RAM expansion or replacement RAM chip for these guys. And since I had a working unit, I thought, well, I've got something to test in a working condition, and I got one that's not working to tinker with. And it occurred to me that all the connections I needed for the Casio 4-bit bus are on this external expansion connector, which makes things quite handy. It's a lot easier to connect wires to here and run them to a breadboard than try to connect to the pads inside the unit. So I thought rather than showing you, the completed connector, I would kind of take you through the evolution of this design, and maybe that would be more useful, kind of give you some ideas of how these things evolve and, maybe the steps, some pointers, some steps that you can take if you want to develop your own connector. So the first thing I did is I found a 10th-inch male header, not like this one. This is a standard one. I found one that was in my junk box that had pins that were 2 to 3 times the normal length. And here's what I've got left of that here, but you can see how long that is compared to a standard one. It's about 50% longer, and it's stuck even further out this side to about right here. So I had that connector, and I tried plugging it in here, and yeah, these are 1/10" spacing, 2.54 millimeters, so that was lucky. But a regular header is loosey-goosey in there. That wasn't going to work. The short side of the long header actually did work, so I thought, okay, this will be okay. And I connected to the other side of it with these DuPont cables like this, and yeah, these stink, especially these cheap ones. The connection's not good. It was a pain in the butt, and I had to worry about with just a raw header like this, I had to worry about accidentally plugging it in backwards and blowing something up, which would be unfortunate. So what I did to help keep it from being plugged in backwards was measure this opening. You can see it's kind of like an inverted T shape. And I designed this little shroud to go over the pin header. The pin header just slips in here. And then I eventually found a scrap of 26-pin ribbon cable. And since I had twice as many wires as I needed, I doubled them up, soldered one to each pin, kept this header on the other end, and was able to plug that into my breadboard. And this works okay. It's not the easiest to plug in sometimes, but I can't get it backwards, and that was important. So that was a good first step. And then I got a hold of a real Casio expansion device. This one's made for TRS-80. This is the printer. And I noticed that these are not square pins. They are in fact rectangular, and they are twice as tall as they are wide. So they are 25 thousandths of an inch wide, 50 thousandths of an inch tall. I'll let you work out what that is in metric, but it turns out that the 25 thousandths wide is the standard width of a square header pin like this. And so, how was I going to come up with pins of this size? And I looked for hours in different connector catalogs to try to find a connector of any pitch with any sort of rectangular pins that size, and I came up with nothing. And then I had the bright idea that I could solder two normal pins together. You can kind of see that here. I get the light just right and can get it to focus. But yeah, there you can just see it. That's two pins soldered together. And I made some of these with a little kind of offset in here. And I thought, well, this might work. It's kind of fiddly to do. And then I made up this little circuit board that has some notches in it right here. And these pins I soldered together set in the notches. And yeah, that sort of worked. It was rather fiddly. And of course, when you try to solder this to this, these heat up and want to separate. It just wasn't very practical. It was maybe better than nothing, but yeah, it was a lot of work. And then I happened upon a thin brass strip that was 1 inch wide, 25 thousandths thick, and about yay long, about a foot or so long. And I thought, oh, I might be able to make some pins out of that if I can cut them the right width without destroying it. And at work, I have access to a small benchtop metal shear. I'll pop a picture up here. I actually bought it for trimming circuit boards, so I don't dull the blade on my big metal shear. But I thought, well, maybe I can figure out how to use that. And the biggest challenge was getting the material fed through the right amount to slice off just this width. So I finally glued together two pieces of aluminum that are about 50 thousandths of an inch thick. And you can press this on the edge of the shear, feed your material in like that, So it touches here. This is the side of the shear. Then you've got the right amount of stick out. You just hold the material in place, remove your spacer here, and cut it. And using that, I was able to get about 80% of these I tried to come out an acceptable width. So that was pretty promising. And then luckily, that was about the right size. I can just cut these in two, and I get 2 pins out of one strip like that, which is nice. So the next evolution then was this design, which is this board here, but with slots going all the way through, and I stuck my brass pins in there. And you can see this is only a single-sided circuit board. But I stuck the brass pins in there and soldered them on. And yeah, that worked okay. It would have been better if the slots were plated through. It would make it easier to solder. But most importantly, that plugged in there fairly decent. And this kind of shape here was just a modification of this earlier guy. So kind of making progress there. I still wasn't really thrilled with this raw brass pin. I didn't want them to, corrode or oxidize. And I thought, well, maybe I can just tin it with some solder. And I did a few of these guys, and that wasn't really that great. It was time consuming. It's hard to get it smooth. And I've heard about this liquid tin plating process for years, but I've never tried it. And when I looked into it, I found you can get a powder which you mix with distilled water. The only place I could find that, it seemed, was being shipped from the United Kingdom, which would be kind of expensive for shipping. And I was able to get this from Amazon or someplace. It's pre-mixed, so you're probably not getting as much solution per dollar, but with shipping, this was a better deal for me. And I'll pop up a picture of me tinning stuff here. The first thing I tried was this new circuit board design, and I'd already soldered a couple pins in it. And I just submerged the whole board in that plating, and it actually worked. In about 10 minutes, you get a nicely tin-plated board, and it did the copper on the board plus the brass pins. I was really happy with that. So I wound up making a lot more pins. Then I designed a new enclosure to house the boards. And when I was happy with that, I had some boards made. And I noticed when even just soldering these 2 pins on this board, it was kind of a pain in the butt to keep them lined up so they're not going uphill or downhill. Then you want them pointing relatively straight. So I 3D printed this simple fixture here, put some Cap-Tan tape down around the parts where it got hot. And this is sufficient if you're going to do a few of these. If I was going to try to do 10 or 20 or 30 of them, I would maybe glue a couple pieces of FR4 together and machine out this shape. That would last forever as a soldering fixture. At any rate, this worked pretty good, and I wound up with this connector. I fine-tuned this shape a little more. It's got a little bump out here where the pins come through, which fits into this little bit of recess that's on the back here, and it provides some more support for the pins. Got a 12-position ribbon cable with connector on it. And one of the overlooked things when you're designing something like this often is the screw length. And I made sure that the total thickness of this with the cover in the bottom was just a tad thicker than the length of these screws. And I wound up using a countersunk screw, a flathead screw, rather than making a pocket here and using like a little button head screw, because this V-shaped section here protrudes less into the lower part. These are number 4 or 2 millimeter will also work. I tried to, these might be 2 millimeter or 3 millimeter. I don't remember. I chose screws, which would be 8 millimeters long, so you could use like number 2 by 5/16 or 2 millimeter by 8 millimeter. That way, no matter where you are at work, because of the ribbon cable sticking up here, I had to modify the inside of this with a little slope. But you can see everything fits in there nicely. This acts as a clamp to hold the wires. If I do another spin on this board, I'll move the through holes for the wires up this way about 1 millimeter, which will make this a little easier to fish out here. What I did is I cut the wires at a slight V, I think about 2 millimeters from here into the center and out to get the right links there. But that gives us a nice connector. It's got a good shape here. It's not exactly like the original Casio design, but it works good for 3D printing, and it gives you a secure connection there. It works really good. For the other end of this, to connect it to the breadboard, I hand wired this little guy here, which was kind of a pain in the butt. It took a long time, but it works, and it is wide enough to go over the bridge here in the circuit board. Make sure I get this plugged back in right, and yep, okay, plugs right in there, and I can connect that to there, and these are polarized, so it cannot be plugged in backwards. And it's another important thing when you're designing a connector is to make sure you have a way to make it polarized so you don't blow stuff up by plugging it in backwards. On this original design, since I kind of had a pocket in here and this part was flat, I printed it standing up, and that allowed these little prongs to come out really nice. They look nice because they were printed vertically, although they're a little weaker because the layer lines come across like this. For this design, I needed to print it flat, so there has to be a little support material under here. And it's probably hard telling on video, but it makes the bottoms of these just slightly rough, but it's not a problem. We'll see when we look at Sven's mains connectors how he designed the connector parts with the 3D printing orientation in mind, which was a really slick way to do it. So getting to this point of, a final usable connector that not only makes good electrical contact, but, is easy to use, isn't, a straight line. You just don't sit down and have one that's working. There's many trials you go through and ideas that don't work out too well before you get, to a final design that works nicely and is not too difficult to build. So this is my development setup for this, not with this particular computer because this is the one with the bad RAM chip, but I'm using the Tandy for that. At any rate, I plug into my proto board, and I've got a PIC development board here, and this is just a two-way transceiver bus latch, and I'm using that because when you're debugging with this development board, when it first starts up, it does some weird things with the port outputs, which can lock up the calculator, or the pocket computer rather. So I have this in here so I can tri-state the outputs that are connected to the PB100 and keep it happy. In the final design though, if this works out, this won't be required. It'll just be this little guy right here. So we're using a PIC microcontroller that has more computing power than this whole thing. Basically, for its 2K of RAM and the logic to decode the Casio bus. And so far I've been using the information from Piotr. I've been able to read information from this as it's accessing the internal RAM chip when it's running a simple program. And I can see it looping through the program, and I'm getting the same data over and over. And now I'm working on being able to back up the entire RAM from this. Piotr sent me a program he wrote for an AVR that did that. And I'm kind of doing the same idea, but a little differently because the way I've implemented it on the PIC. So let's have a look at Sven's mains connectors now. Here we are on Sven's website, and we'll first take a look at the European VIC-20 power connector for the earlier VIC-20s that only took 9 volts AC. Now, these are different than the American connectors, which used a slightly modified mains connector, which is unfortunate because somebody not in the know could accidentally plug it into the mains. The European version is square with this slot in the middle, but it does keep you from accidentally plugging the mains into it. And he talks about the first thing he did was find the right terminals, which were a snug fit for the prongs on the connector. Then he got the basic design of the housing down so it would be a snug fit. And here's the clever bit that he did. He designed this connector to print in 4 parts and laid these out in the orientation that was best for 3D printing. In other words, this nose part, the prongs that stick into the connector on the VIC-20, are designed to print with this on the base of the printer, so you get a nice profile without needing any support. Of course, this prints with the bottom down. You've got the clamp here, then you've got the top, which screws onto the thing. Here's a nice side view of that. Here's all his parts printed out. And again, he's thought about the length of screws that are needed to put all this together. He makes a really good point about the holes that are 3D printed holes not being an exact size. They're usually a little smaller. So he drills those out by hand to get the right fit. And he makes a very good point about using the right crimper for the terminals that are used. This can be a little tricky, finding the right crimper for the right terminals and not spending a boatload of money on a crimper, but it is important. You see a lot of people trying to do these with pliers and then solder it on, and you can't do that because you notice that the back of these terminals actually crimps over the insulation. This provides a strain relief. If you solder this, the solder is going to wick back in here, you're going to melt it here, and you'll wind up with a really weak point where the solder stops and the copper wire starts. That's where it'll always break if you try to solder these. Here he shows it assembled. The wires split around where the screw post goes. It's got a nice strain relief here so you're not wiggling the wires at the connection. And then he shows the assembled unit and plugged in, and everything works fine. And he said that the trickiest part here was getting the shape of this right where it plugs into the connector on the VIC-20 so you have a nice secure fit. And here is the link to that design on Thingiverse. Now, his other connector here was for a Commodore calculator, and it used what I think he called a Japanese calculator mains connector. And here you can see it's a 3-prong mains connector. And again, he started out finding the right terminal that would fit these posts. And he had to find, the closest one he could that would make it fit, and then did a simple test. Of course, this is dangerous because you've got live wires here, and it's a good time to point out that you're working with mains voltage here. If you don't know what you're doing, don't attempt this yourself. whereas with my connector for the pocket computer, the worst thing that would happen is you would blow up the pocket computer. With this, the worst thing that would happen is you blow yourself up, which would be much worse. So just be careful. And then he started designing a housing for this. Even modeled the terminals. We've got a nice cutaway view here. Nice mechanical drawing of the housing. And again, he has designed this keeping in mind how it's going to be printed, like we saw in the VIC-20 connector. Very clever way to do that. Here is a nice view of the bottom of the connector, and he's got 4-screw posts here, so it's nice and secure. Here is the assembled connector. See, he's even thought of how to get the wires through there. All the things you got to consider. Consider the types and lengths of screws to be used. The screws are flush on the top. You get a nice looking connector, and it plugs in and it's nice and secure. And again, he's pointing out here that you could hurt yourself with this if you don't know what you're doing. So be careful. If you don't know what you're doing, get help from somebody that does. And here is the link to this design on Thingiverse. And thanks to Sven for sharing this and going into some detail about why he designed things this way. That's very helpful for other people who might need to design their own connector. Well, I hope this look at designing your own connectors for vintage devices has been helpful, and maybe it'll give you a few ideas. I'll put the links to my design for this and to Sven's website in the description down below, as long as where I found this stuff. And you can find the powdered version in various places. Just search for the liquid tin or electroless tin plating, and you might be able to find links where you are at in the world. If you have any questions or comments, well, just leave them in that comment section down below. I would love to hear from you. And as always, I'd like to take a second to say thanks to everyone who helps support the Hey Bert channel through Patreon and other means. It is greatly appreciated, and you keep this channel going. Well, until next time, bye.